I'll be talking a little bit about brain-machine interfaces and some of the recent developments in neuroprosthetic devices. Now, very often in systems neuroscience and brain-machine interfaces, we use an initial task and we try to correlate or understand how the brain is processing that particular task. So let's imagine that we have a monkey, for example, controlling a cursor in XYZ direction, and as he's watching his arm or a virtual arm doing it, we have electrodes in its brain. What this means is that if the brain works by electrical activity or part of it is electrical activity, then we should be able to measure these differences in electricity. Now, if we have one electrode, we can measure it in one place. But if we have multiple electrodes in multiple places in the brain, we can analyze many places and see what's happening in a broader scale. So we do this in real time as the monkey is doing a task. And we can see, for example, here an example of a cell that is firing for a particular event. Let's imagine that at time 0, something is touching the monkey's paw, and you see an increase. That huge peak is an increase in activity. Now, if we have multiple electrodes, what we can do is we can now look at multiple cells. We can now combine the activity of all these cells, and you see on your right panel that each line is one of these cells. And if it's in blue, it means that it has low activity, very few spikes or very few action potentials. But if it's yellow or red, it means it's a lot of activity. So if you look at all these cells, what you see, and this is going to be really important, is that the majority of cells seem to have an increase in activity after time 0, but not all the cells are doing the same thing. And this is really important for brain-machine interfaces. What this tells us is that regions tend to do mostly one thing, or they may primarily do one thing, but they can do many things.